Remember that bacteria problem where we had to use guess and check or trial and error to solve that one particular part of that problem? The way that we are able to solve that question algebraically, not just with something like trial and error, is using something called a logarithmic function. First, we have to do some study of logarithmic functions before we can go back to that problem and actually solve it. We have to know what logs are and such. That's what we're going to do in this video. We are going to learn how to change between logarithmic and exponential functions. We're going to evaluate logarithmic functions, basic properties of logarithmic functions. Then we'll do a little bit with graphing logs, domain of logs, and then common and natural logs are things that we need to recognize. So those are our goals for this section. First, let's define a logarithmic function. It might be a good idea at this point to go back and review inverse functions from back in Unit 2, because a logarithmic function is the inverse of an exponential function. So if you feel like you aren't quite clear on what that was, go back there and just look through your notes before we move forward here. Pause this video and go back and refresh. Excuse me. The inverses of exponential functions are called logarithmic functions. We said that. What does that mean? Well, what it means is that y equals log base a of x is how we say that, if and only if a to the y is equal to x. So a traditional exponential function would look like that, right? Remember, with inverse functions, we switched the variables and we would get something like x equals a to the y when we switch the variables. Well, that's what we have here, right? A to the y is equal to x. So that's why these are called inverse functions, or these are inverse functions of one another. Notice that the y, which is what the log is equal to, is the exponent that you put on a. And that's what this little statement over here says. Logs are exponents. Think of them as the exponent you need to put on the base, whatever this base is, the exponent that you put on that to get what's inside the log. Let me show you what I mean here. Log base 2 of 8 is really asking 2 to what power is equal to 8? And that is 3. Since 2 to the third equals 8. Okay? Here, log base 7 of 7 to the 1/2 power is asking 7 to what power, that's a question mark, is equal to 7 to the 1/2. And that is, of course, 1/2. What exponent do I need to put on the base, this guy down here, to get what's inside there? Sometimes I think of this in sort of a circular pattern. Let me write this one this way. In my brain, because I'm pretty visual, I tend to do this graphical loop kind of thing. Not really graphical, but this visual loop kind of thing. 2 to this power equals that. Here, when I have log, let me rewrite this, log base 7 of the square root of 7, I said that was equal to 1/2. I'm picturing in my brain here. 7 to the 1/2 power is equal to that. Okay? Let's look at this one. Log base 3 of 1/9. 3 to what power is 1/9? Well, it's going to be -2, right? Log base 3 of 1/9 is equal to -2. The log is equal to the exponent that you put on the 3 to get 1/9. Sometimes you will see a log written without a base. That doesn't mean that it doesn't have a base. You have to have a base. You have to know what you're putting an exponent on. But it is 10 is what is implied by that. And that is called the common log. This is asking log base 10 of 1,000. What is that equal to? Well, that's going to be 3, since 10 to the third is 1,000. So that log is equal to 3. One other log that is seen frequently is the natural log. And that is a logarithmic function with base e. So there's nothing really to do here, to simplify here, because this question, when we say the natural log of 5, that's asking e to what power is equal to 5. Well, the problem with that is that e is an irrational number, right? So the exponent that would need to go there is the natural log of 5. It doesn't simplify. We could approximate this, and your calculator will do that. Let me clear this stuff out. The natural log button on the standard graphing calculator, the TI graphing calculator, is here. So if we do the natural log of 5, hit enter, that's an approximation of this. It is approximately 1.61. So approximately 1.61, but I don't want you to say it's equal. The natural log of 5 does not simplify. It is an irrational number. What that's saying is e to the 1.61 will be approximately 5. And you can kind of check that over here if you use your exponential function. Here, e to the x is the second of that natural log. 1.61, pretty close to 5, right? Little rounding error. Okay, but this one that we see here will actually simplify, because you are asking e, when you see a natural log like that, it's base e. E to what power is equal to e to the 6th? And of course that answer is 6. So the natural log of e to the 6th is 6. We're going to do some more practice converting back and forth between logs and exponentials. That's what we were starting with logs here and basically converting them to exponentials to figure out what we needed. So we're going to do the same thing here, but the other way. Start with an exponential and go to a log. Log, the base, which is a subscript on the log, the base on the log is the same as the base on the exponential function, so it's 7. The exponent is what the log is equal to, and then the 49 is what's inside. Remember, that's completing that loop that we talked about. 7 squared is 49. So your answer here, and I just drew through it, but your answer, the log that corresponds to that exponential equation, is that logarithmic equation. Log, base is 3, 16 goes inside, the x is the exponent, so that's what the log is equal to. The base of the exponent becomes the base of the log. The exponent is what the log is equal to. The x is inside. This would be log base e of 18 is equal to x. The exponent is what the log is equal to. But this is not how we would typically see this written. We would not typically see log base e written. We write that as the natural log of 18 is x. Okay? Let's go the other way. Log base 4 of 64 is indeed equal to 3 because 4 cubed is 64. The base on the log becomes the base on the exponential. What the log is equal to is the exponent. 6 to the x equals 8. Make your loop. 6 to the x equals 8. Here, e to the 6th is equal to x. That base is just kind of hidden in there with that natural log. Let's do some basic properties of logs. Log base a of a to the x. We saw this several times up above. Let me show you where we saw that. We saw it here where we had the natural log of e to the 6th. Remember, that is log base e of e to the 6th, where these two things match, right? We also saw it up here when we rewrote this. The 7 and the 7 match. Notice in both cases, the exponent on what's inside was what that log was equal to. Same thing here. This ended up being equal to 6, that exponent. So coming down here to this property, log base a of a to the x is x. If you make that loop, you get a to the x is equal to a to the x. So hopefully that makes sense. Here, that means this is 2 and this is 1, because that 4 is 4 to the first power. 4 to what power is equal to 4? Well, the answer is 1. Similarly, of having an exponential inside a log and having it simplify to the exponent, here when you have a log inside an exponential, it simplifies to that x. So this is 5. That one we don't see as often, but it could still come up. And that also gets us back to the idea that the exponential function and the logarithmic function are inverses of one another, right? You plug in an x, you run it through the exponential function, you run it through the log, you get back to x. Here, you plug in an x, you run it through the log, and then you run that through the exponential function, you get back to x. It goes back to that definition of logs and exponentials being inverses of one another. Log base b of 1. Remember, we are asking b to what power is equal to 1? Well, that's going to be 0 for anything that b can be. The base here has the same restrictions that it does on the exponential function. It has to be positive, and it has to not be 1. Log base 17 of 1 is 0. I think this is a good place to wrap up this video, and then we'll come back and talk about what do graphs of logarithmic functions look like in the next video. You can take a little breather now.